Hey guys, Ms. Shootman here, and this should be the first video that you're watching. This is on chapter 15. We are going to be finishing up. So previously in class, we had talked about 1 minute and we also talked about 1 second arcs. And you should have done some practice with that. We had a practice assignment. Now I'm going to continue talking about length of arcs. We're going to be able to find areas of sectors. We're going to be able to find areas of wedges and so forth. So this video will take you all the way through the rest of chapter 15. So an important fact, the length of a part in general is going to be the fractional part times the whole length. Okay, so if you're ever trying to find the length of a part, you take the whole part and you multiply it by the fractional part. Again, this might not make sense quite yet, but I think it will so here in a little bit. So for example, the circumference of the entire circle of a radius r is 2 pi r, right? The circumference being the outer perimeter of a circle, essentially, aka, think of this as the length of whole. Right, the whole thing is 2 pi r, right? So 90 degrees, right? 90 degrees, that's the fractional part, over the whole would tell you that we've got 1/4 of the entire circumference. Right? So if you wanted to find the length of the part, right, again, you would use the fractional part times the whole length. In this case, we're kind of doing it differently where we're going, right, 90 divided by the 360 because this is the part, this is the whole. This tells you the fractional part right here. Okay? So this is just one example. Important fact, arc length in degrees. Start with the central angle of measure, theta. Okay, so we are going to be using theta whenever we don't know the angle of something. We're not going to be using x, we're going to use theta, degrees, inside a circle of radius r. Then this angle will subtend an arc length. I'm at school, by the way, that was the bell for third lunch. Okay, so then this angle will subtend an arc length. All right? So if you're like, what does the word subtend mean? I can visually show it to you. So what you would do is you would maybe want to draw a wedge like this, right? And here is the arc, right? And so I'm going to note that the angle subtends the arc. So this is like a visualization of what that actually looks like, okay? You could say that in a way the angle is like inside the arc, kind of. I guess is a way to kind of think of the word subtends. But subtends is the word that describes what the angle is doing to the arc, okay? And this is a visual representation, this part being the angle and this part being the arc, okay? So you guys, I'm going to turn on to the next page. If you need to write this down, you'll want to hit pause. So what you guys need now is the arc length formula. Okay, so this is the arc length formula. And this is the formula you use when theta is in degrees. Okay, this is what you use when theta is in degrees. It will not work if it's in radians. Okay, so S equals pi over 180 r theta. All right, and I'm going to label a couple of things. S is going to be what we use, the variable we use when we're talking about arc length. Okay, so S is arc length, right? The radius is r, that should be obvious, it's always been r, it will continue to be r, right, radius. And then again, theta is going to be angle measure in degrees. Now, what happens if you have an angle measure for theta that's not in degrees and it's in radians? I feel like it should be kind of obvious, but if you don't know, I'll explain. If theta is in radians, then you simply get rid of the pi over 180. So it would just be arc length r theta. It makes sense because think about what pi over 180 does. Pi over 180 converts, right, degrees into radians. Think about this. If you plug in, for example, 180 degrees right here, right? The 180s will cancel, leaving you with just pi, which is now radians. So, I will repeat it one more time. If theta is in radians, it is the same exact equation except for the pi over 180. That's the only part you take out, okay? And I'm going to go ahead and box this so it stands out in my notes, and you should probably do the same, all right? So now what I'd like you to do the best you can on this, draw a circle. Do your best circle that you can draw, and it's not perfect, it's fine. I mean, mine isn't perfect. It's actually not too bad though, considering. So there's my circle. Again, not perfect, but good enough. And if your circle's super wonky, whatever, hit pause, do whatever you need to do. And what I'd like you to do is figure out where the center of your circle is. I'm going to just say it's right here, right? And we're going to call this side the radius, right? Because, I mean, it is. If you're ever starting from the center of the circle and you make it out to the circumference, right? That is the center. And I'm actually going to go ahead and draw another radius right here, another radius line. Remember, you could draw an infinite amount of radius lines in here, right? It's basically, like I said, a radius is any time you go from the center of the circle to the outer perimeter of the circumference, okay? So I just want a visual of this. This part here would be considered theta, right? And this part out here would be considered the arc length, right? And we could call this, I'll write arc length, which we already know, or also known as, so AKA, distance along arc. Distance along arc, okay? So this is just kind of a visualization of what's going on here. And I don't know if this is blurry yet, so I'm going to redo that real quick, okay? So, 90 degrees, right? If you use that equation, S equals pi over 180. That was weird. R and then theta. That's the equation we would use, right? But we know theta is 90, so we would go, right? This would turn into 90 pi, which is really over 180. It's really pi over 2r. That's what this would simplify to be, right? Because you have 90 over 180, that'd be a half pi, or pi over 2, right? So the arc length of 90 degrees is pi over 2 times whatever the radius is. And think about why that makes sense. You can draw a circle any size you want, right? This is the circle I decided to draw. This is the size I decided to draw out. I could have very well drawn a circle that's this size, right? And let's pretend that that's actually like a legit circle, right? I could have drawn a circle that was this size around, right? I mean, I could have done all sorts of different things. So the arc length is really dependent on the radius of that circle, right? Because obviously, the smaller the circle, the smaller the arc length. I mean, if I even went with this circle next, right? And if I did the same degree wedge, it's like, let's pretend that this is kind of centered. This is a hair tie, so it's not perfect, but you get it, right? Here's the center of the circle. If I extend this radius out, we can see this arc length is going to be bigger than this one, right? And then if I go and I use, let's see, so many circles around. Here's a lid to a candle, right? Now if I go and use this, for example, right? Same thing, this is like the center of my circle, right? And if I draw like the radius out like this, right? This arc length is going to be way bigger than this one, right? So the radius does come into play. That's why you have to take that in consideration when you're dealing with arc length, okay? So what I'd like you to do now is I would like for you to get this information either copied or cut out if you're one of those students that has your notes printed out in advance. Okay, so here's this. And hit pause right now if you need to capture this, okay? Also, similarly, right here, go ahead and hit pause to capture this. I'm obviously not going to give you time to do this because you can hit pause and copy it, all right? So you want to have this picture. And the thing that I need you to note on the side, okay, is that right here, this thing that you see right here, this is a basic wedge. So this is a basic wedge where all three sides have equal length r. If you look here at this picture, and it might be a little hard to see, this is saying this is r, and this is r, okay? This angle is defined to have measure 1 radian. So we've used the word radian before, and you maybe had no idea what a radian actually is, right? Degrees we can wrap our head around. We're used to that. We learned about it in geometry. But radians are a little bit tougher. What is 1 radian? 1 radian wedge is when all side lengths are the same. This length is r. The arc length happens to be r. This other piece is obviously r, right? I mean, this part is a duh, right? Anytime you draw a radius, it's going to be the same, right? So this is showing you that they all have the same length. We can also call that an equilateral wedge, right? And that again should make sense. You think of the word equilateral, back to your geometry days, an equilateral triangle has 3 equal side lengths, right? I mean, it, again, makes kind of sense. So an equilateral wedge would have 3 same side lengths, right? So once we define an angle of measure to be 1 radian, so once we define an angle of measure to be 1 radian, for example, we can define an angle of measure for 2 radians by putting 2 1 radian wedges together. Well, an angle, that's kind of weird looking. We can define an angle of measure for 2 radians by putting together 2 1 radian wedges. Which again should make sense, right? Like if this right here, if this thing is 1 radian, 2 radians would be me taking 2 of these and putting them together, and so forth, right? So going down to this detail over here, and again, if you needed this, hit pause, okay? Important fact 15.4.1, arc length and radians. Start with the central angle of measure theta radians inside a circle of radius r, which is what's going on in this picture here. Then this angle will subtend an arc length of s equals theta r, which we already know. If you're trying to find the arc length, this is the formula you use. This is the formula you use, though, when theta is in radians. You might have already written this in your notes, right? Because if you remember, this was the equation we use when angle is in degrees, which makes sense because then we're going to convert it by multiplying by pi over 180. If it's already in radians, no extra conversion is needed. These remarks allow us to summarize the definition of the radian measure theta of angle AOB inside a circle radius r by the formula, okay? And this is hard to see, so I'm going to go ahead and write this out for you. Theta equals s over r, okay, if the angle is swept counterclockwise. It is negative s over r if the angle is swept clockwise. That should make sense. We've already, and I'm actually going to rewrite this bigger because it's bugging me how small that is. S over r, okay? So we're going to go negative s over r if it's swept clockwise, which makes sense. What we've already learned about angles in standard position, right? If we ever go clockwise, it's going to be negative, and if we ever go counterclockwise, it's going to be positive. So you can think of theta as being just s over r, and if you think about that, that's obvious. You can derive that from this, right? If I said, hey guys, figure out theta, and you had r and you had s information, you would know to divide both sides by r, right? And that would get theta by itself. So this is just a derived equation that you could have derived from just right here, okay? And again, it's this way when we are in radians, okay? Defining an arc length here, and again, this is just a picture, a visual picture of what's going on, okay? And again, this is R, I know this is kind of hard to see, this is S, right? Which again, we know that already. You might be wondering what this says. This says C sub R, and basically this is the circumference for the radius, for this particular radius. So this is C sub R, okay? And this again is defining arc length when angles are measured in radians. This is just a visual representation of what's going on. And again, we talked about the circumference of the circle or the length of the radius makes a difference on the arc length. The smaller the circle, the smaller the arc length. The bigger the circle, the bigger the arc length. Okay? Hopefully that makes sense to you. So for the next part, it's kind of weird. I am going to have you guys post up these pictures, but there's no notes to take. So this is just a visual representation of what we previously talked about, where if I communicate that this is a radian, it is a radian because all of the lengths of the wedge are the same length. 2 radians would be taking 2 of them, putting them next to each other. 3 radians would look like this, right? If I said half a radian, you would envision a whole radian and then splitting it in half. And then a 4th radian would look like this. This is just visual representation of what we've already talked about, okay? And then here is showing you guys another way of thinking about common angles measured in radians. So if you think of basically a circle being able to be divided into 12 parts, right? This would be pi over 6. This is what this rotation would be. This would be pi over 4. This would be pi over 3. This would be pi over 2. This would be half a revolution, right? Half a revolution being pi, right? A fourth of a revolution being pi over 2. And you might be saying, wait, why is a fourth revolution pi over 2? Because remember, the whole thing, to here at least, 1 whole pi is here, right? So remembering that a full rotation is 2 pi. And again, this is showing, right, half the revolution being pi. This is showing 3 over 2, right, 1.5 pi, right? It's 3/4 of a revolution here, right? So this is, again, just the visual representation of what's going on. This stuff will help you more when we talk about unit circles. Again, if you have not studied or looked at a unit circle yet, you should probably do so. So I totally forgot to hit pause, which sucks, and you obviously heard me cutting and doing all that fun stuff. So here we are with areas of wedges. So I guess hopefully you fast forward and I just type in when you do that. But anyway, so here it is, areas of wedges. Example 15.5.1, right? So this is the example I'm dealing with, and this is kind of the next part of chapter 15. If we have a 16-inch pizza that is cut into 12 equal slices, what is the area of a single slice? So the thing that I'm going to need you to recall is that, again, remember that the area of a part is the area of the whole times the fractional part, right, times the fractional part. Okay, so you need to recall that information, right? I need you to also note that the area of a circle is pi r squared, right? And so since our pizza is 16 inches, we know that the radius is going to be 8 inches. Or maybe you didn't know that. So whenever you say that you're getting a 16-inch pizza, that's basically going to be the inches of the diameter, right, all the way across. So the whole thing, if you were to measure it from one end of the circle to the other, you would get 16 inches. That's a 16-inch pizza, right? So if that's the diameter, the radius would be half of that, which is 8 inches. The thing you need to remember also when we're dealing with the pizza, they cut those into 12 slices, traditionally, right? Means, and actually in this case, it's 12 equal slices. My bad. I shouldn't say that all pizzas are cut 12 ways, because I feel like you could actually cut it in 8. But in this particular situation, we know it's a 16-inch pizza cut into 12 equal slices. So 12 slices means, right, that one slice is a 12th, right? One of the 12 slices, right? So if I'm trying to find the area of a single slice, the area of a single slice is going to be, right, pi r squared, which is the area of the whole pizza, right? Area of whole pizza. Again, area of a circle, pi r squared. The radius is 8, right? So if you're following along here, again, if we're trying to find the area of a part, you're going to take the area of the whole dang thing, which is what we have here, and you're going to multiply it by the fractional part. And so the fractional part is that it is a 12th, right? A 12th. This is the fractional part. And that's going to end up being, well, 8 squared is 64 pi times a 12th, right? That's going to end up simplifying out to be 16 pi over 3, or approximately 16.76 inches squared. Now you might be saying inches squared. Hold up, where did the inches squared come from? Well, wasn't the radius in inches? And if you're going to square the 8, you have to square the inches too? The answer is yes. That's where inches squared came from. So if I really want to do this right, I really should have written 8 inches in parentheses squared, so that I would then square it from there. Okay? So we're going to go back now and draw another picture of a circle. Maybe this time, I don't know, my circle last time turned out pretty good. Something tells me I'm not going to be so lucky, but we'll see. Not too bad. I'm like really surprised that my circle drawing skills are not that bad, actually. I thought they were going to be way worse. So draw a circle, and right by this, I am going to write that this is the area of a circular wedge. Or sorry, a circular sector. Circular sector, okay? And what I'm going to do in this picture is I'm going to figure out where I want the center of the circle to be, which is going to be right there for now. And I'm going to call the center of this circle O. And I'm going to call right here, I'm going to call that B. And I'm going to call this A. Okay. And I'm going to label the radius here, right? And I'm going to draw a little angle here, right? And I'm going to write that the circumference of the whole thing is CR, which we've already talked about, right? And I'm going to, in addition to this thing, I'm going to call this whole wedge, okay, this whole wedge, is going to be r theta, r sub theta, sorry, okay? So I'm going to write here off to the side. Let r sub theta be the pie-shaped wedge cut out by angle AOB. Now mind you, order matters when you're talking about angles. You could call this also the same angle BOA or angle AOB, or you could call the whole angle angle O, but you cannot call this wedge right here BAO, because again, if we're following the order, it's not great. So you want to make sure you do it in the right order. Again, AOB works, BOA works, or just angle A. Angle O. My apologies. And I forgot to also write, with positive measure theta radians. Okay, so this is kind of just visually showing everything, again, in a different way. Okay, so if I wanted to find the area of capital R theta, R sub theta, sorry, it would be the area of C sub R, and I'll keep it little r to keep it consistent here, times the portion of R sub theta. And again, remembering theta over 2 pi. But that's the whole, right? If the whole thing is 2 pi, you've got to write whatever portion it is of it. Okay? So that's that when it comes to area of wedges. I'd like to next talk about 15.52 and example 15.5.3. So for that part, here we are. Okay, so important fact, start with the central angle with positive measure theta radians inside a circle of radius r. The area of the pie-shaped region bounded by the angle is half r squared theta. Okay, so this is an important fact about wedge area. And then we've got this example. Example 15.5.3. A water drip irrigation arm, 1,200 feet long, rotates around a pivot P once every 12 hours. How much area is covered by the arm in 1 hour? In 37 minutes. How much time is required to drip irrigate 1,000 square feet? So there are a whole bunch of things going on here. You guys, we're bringing it back to the what I know and what I'm finding. So go ahead right now and make a list of what you know. So what I know, ... and what I'm finding. We haven't done one of these in a while, and it's definitely time because there's a lot to unpack here. I would go ahead and hit pause so you can do this list yourself, because as soon as you hit unpause, I'm going to be showing you actually all the way. All right, guys, here's my list. So what are some things I know? I know that the radius is 1,200 feet. You might not have known that because you might not have understood visually what was going on here. But when it says a water drip irrigation arm is 1,200 feet long, I mean, basically you would have wanted to envision, right, there being a center and there being an arm and this thing rotating, and it basically has holes in it that have water dripping out. Again, you might not have been able to visualize this because you maybe don't even know what an irrigation arm is. And of course, if you didn't know that, that's not your fault, but here I am explaining it to you, okay? And of course, they talk about the pivot P, so I mean, you can envision maybe this is point P and then there's the irrigation arm rotating, right? One thing that I know you should have been able to pick out is that it rotates one full revolution 12 hours. So you can imagine if I started here in 12 hours, I would end up right back where I started. This is something that you didn't have written on here, but you need to think about. One revolution is also 2 pi radians. You could also say one revolution is 360 degrees, but we really need to start thinking about things in terms of radians. We need to really get away from degrees, okay, guys? So one revolution, one full rotation happens to also be 2 pi radians. If you didn't write that down, please jot it down. And then T is time in hours. So these are the things I'm noticing and I'm noting, all right? Now for questions, they want to know these 3 questions. I'm not going to repeat them because they're there, okay? So if we're wanting to get started, this is going to bring us back to Unit 2, unit conversions, okay? We always want to start with the information that we know, and we need to consider where we want to end. So where am I starting? Well, I know that this thing does 1 revolution every 12 hours. I know that, right? Because I'm trying to figure out the area after 1 hour, right? So I'm just going to at least start with 1 revolution in 12 hours. And I know the game plan is to, at some point, figure out an area, right? So what I'm going to do first is I am going to get rid of revolutions, because revolutions / rotations, you can think of a revolution as being like a rotation, that's great and all, but that's not giving me a unit of measure, right? That's just telling me how many times it turns, right? And I need to really get rid of that. So I'm going to multiply this by 2 pi radians over 1 revolution. Now the reason I'm doing that, first off, I can do that because 2 pi radians is 1 revolution. These are logically 2 equivalent things. And I'm writing it in this way because I'm wanting to get rid of revolutions, and there's my way of doing it. And not only am I getting rid of revolutions, I am now bringing in units of actual measure, right? So now that's going to leave me with 2 pi radians over 12 hours, right? Well, this can simplify down. That's going to be just pi over 6, right? And this is radians per hours, right? So we basically know that this thing rotates essentially pi radians every 6 hours. But really, we could write it like this, which is even better. It rotates pi 6 radians per hour. This is another way of thinking about it or writing it, right? So, going back to, we are trying to find the area. We are trying to find the area that is covered by the arm in 1 hour. We need to come back and look at that wedge area equation that we were just working with previously, okay? And I'm going to write it in this way. I'm going to say the area of the wedge is going to be A of t. That's what I'm going to just call it. And remember, in general, it's a half r squared theta. And remember, theta needs to be in radians. Okay? So now I know what the radius is, right? I mean, we were given that information out the gate. So it's going to be 1200 squared, right? And then times a half, because that's what's in the equation. And theta in radians is pi over 6. And then from there, this is basically 120,000 pi feet, right? Because that's what this squared is, and then divided by 2 and everything. This is what I'm getting here. And that's going to be approximately 376,991 again, wow, I'm just messing this up constantly, 1184 feet squared. Again, why feet squared? Because this radius was in feet, and then you squared, and there it is, okay? So there's our answer for part A. But part B, right, part B, there's a slight problem. For part B, we're not doing a full hour, right? For part B, they want to know after 37 seconds. So guess what? I'm going to have the same initial setup. I'm going to have a half times the radius, and I'll this time write feet. Okay, I'll write feet this time just to make it better so you can see where it comes from. Over the radius, right? But this is where I'm actually trying to figure out a fractional part. 37 minutes per hour, right? 37 minutes in an hour. So this is the fractional part piece right here. Okay? Previously, I didn't have to do that because this was per hour. This was per hour. So it's good to go, right? But I can't leave this like this anymore because it's not per hour. I want to figure out what happens at 37 minutes, right? So there's my work, guys. When everything's said and done, you're going to end up with 74,000 pi feet squared. Or, because if someone tells me, oh yeah, the area that was watered was 74,000 pi feet squared, I'm going to be like, huh? But if someone told me 232,477.8564 feet squared, I could actually wrap my head around that a little bit better. Okay, so there's your work for part B. For part C, how much time is required to drip irrigate 1,000 square feet? So what I had basically rewritten this as is, what's T when A of T equals 1,000 feet squared? So for this, I would set up, right, they want to know what's the time when it's 1,000 square feet that's been measured, right? So I'm going to go ahead and take my equation here. Whoa. And this was right here. Sorry, this is per hour, right? So 20. I have enough zeros. 1, 2, 1, 2, 3, 4. Yep. Pi t, right? So basically I know that that is the amount, right? That's the amount of feet. So if I'm trying to figure out how much time that is, I'm going to go ahead and divide both sides by this 120,000 pi. Whatever I do to one side, I'm going to do to the other, right? This cancels out, and I'm going to end up with 1 over 120 pi equals t, right? And I want to actually be able to wrap my head around that. So this is going to end up being 0.00265 hours, right? So that's what this ends up being. But they want to know how much time is required to drip. They said time. I guess you could leave this, but I don't know about you guys. I don't know what 0.00265 hours is. So I'm going to convert this into maybe minutes or seconds. And I think I'm actually going to go seconds, because I have a feeling it's obviously not going to be, hours isn't going to be helpful, right? And I know that there's 3,600 seconds in 1 hour. That's just a unit conversion we used all the time, right? And this is going to tell me that it's going to be approximately 9.54 seconds. But that's how much time it's going to take to reach 1,000 square feet, which is pretty nuts, but not really, right? So the next question that we're going to do, or the next part we're going to do, is 15.5.4, and this is the last. All right, so here's the last problem. Example 15.5.4. Estimate the distance from R to S. And if you can't make this out very well, this is R, this is S. This has 5 degrees written right here. This is 20 feet. If you're wondering what this little scribble is, this is supposed to be a picture of a dog on a leash, right? And that the leash is connected to like a, I don't know, stick. I don't know what you would actually call that thing that's impaled into the ground. But basically it's connected to this, right? And basically the dog can run the circumference essentially, right? And what we're trying to figure out is this distance from R to S, okay? So how do we go about doing that? Well, luckily it's pretty straightforward. Recall that arc length, right, again, is pi over 180 r theta if we're in degrees, which by the way we are because we're given 5 degrees, right? So I simply just plug in the numbers. The radius happened to be 20. So there it is. Theta was 5, right? So when I simplify this out, this is going to end up being 100 pi over 180, right? Because 20 times 5 is 100, and then, yeah, there's that. And this is going to end up being 5 pi over 9, or 1.7453292252 feet. And I'm going to say feet because that's the unit of measure that we're in. And this should be in feet as well, okay? And this is that straightforward. Now, I don't know if I've already assigned a book assignment 15. If I haven't, I have it right here for you. I'm going to tape it up. I definitely miss my paper cutter because I don't cut very straight without it. But there it is. It's going to be on page 205 to 206, 15.3, A through D, 15.4, 15.5, 15.7, and 15.9. You will want to watch the next video on chapter 16, and you'll also want to do any practice for chapter 15 as well if you have the time to do so. I would highly recommend it. There is some practice, I think, on finding areas of sectors, which is this basic skill right here that I think you should give a shot as well. So there it is. If you have any questions, feel free to hit me up on the chapter 15 discussion board. I have been really bad about looking at the discussion board, particularly for chapter 13, 14. My apologies on that. I will make a conscious effort to check that thing every day at least once. So I should be able to respond to you within 24 hours. Anyways, there it is. If you guys need to watch this over again, or if you have questions, make sure to write them down in the discussion board so I can help answer them there. Hope all is well, guys. Don't forget, you got one more video to watch on chapter 16.